In my last video, I started to investigate the system of phase transformations between these three imaginary mineral forms, these three crystal structures of a single chemical composition for some imaginary mineral. I want to understand when each of these three crystal structures was the favored one, the stable crystal structure, compared to the others. That is, at what temperatures, at constant pressure, did each one have the lowest Gibbs free energy? And what we found was that for temperatures under 237 Kelvin, the anorite form had the lowest Gibbs free energy, but at 237 Kelvin, its Gibbs free energy was equal to that of iseldite. And above that, iseldite was the lowest Gibbs free energy, the stable form, until 893 Kelvin, at which point elendite became the stable form. And those were the results we came up with last time. And we came up with them essentially by using this equation. I don't know if I wrote it in exactly this form before, but we said we used the thermodynamic identity for the Gibbs free energy at constant pressure, so dP is 0. We integrated it, and then rather than just looking at Gibbs free energy as a function of entropy, we said what was the difference in Gibbs free energies between anorite and iseldite? And we subtracted that, and so the difference, and we subtracted the two, and that gave us a difference in the two Gibbs free energies at our reference temperature minus the integral of the difference in their entropies, dt. And at the phase boundary, TAI is the phase boundary here at 237 Kelvin. At that phase boundary, that difference in their Gibbs free energies was 0. That's what a phase boundary is. It's when the Gibbs free energies are equal. And so we did that, and we solved for TAI. Now we did that by assuming that the difference in entropies was constant, so that this turned into an integral of a constant. The constant could factor out. It was just the difference in entropies times the change in temperature, and we were able to solve for TAI that way. There are two things that went into this. First of all, we did this in terms of differences specifically because we were worried that the entropy of each one individually would not be approximately constant over the temperature ranges that we cared about. I want to investigate that in this video. But we did assume that the difference in entropies, the difference in the two entropies would be approximately constant over the range we cared about. I want to investigate that too and figure out how to do better if we need to. Let's look at this. And so is entropy constant? That's a good place to start. Is the entropy constant for this system? Well, let's look at anorite in particular, just because I've got it here. Anorite, if I want to look at its entropy, I can look down here. I've copied down the classic thermodynamic definition of entropy. Well, it's not the definition once you do statistical mechanics, but our core relationship between entropy and heat is ds, changes in entropy, are equal to a tiny bit of heat divided by temperature. dq, that tiny bit of heat, is just the specific heat times dt over temperature, specific heat per mole, divided by temperature. And so if I want to find a finite change in entropy over a finite temperature range, I just integrate both sides of this. I clearly, because this depends on 1 over t, I can't just turn this into a delta t because it's a 1 over t. I've got to integrate both sides. So I can write that the integral ds anorite from T naught to, I'll call it TAI. Why not do that specific temperature? Why not? That integral should equal the integral from T naught to TAI of this thing, my specific heat dt over T. I have to integrate. And when I do this, now I'm in another bind because I have an unknown specific heat in there. If I assume the specific heat is constant, which I will in this case, it often isn't, by the way, but if Cp is approximately constant, and again, honestly, differences in specific heats are going to be closer to constant. I'll say more about that in a minute. But if Cp is approximately constant, then this gives me the left-hand side is anorite's entropy at temperature TAI minus anorite's entropy at temperature T naught should be approximately equal to Cp, factor out the constant, and the integral of t dt, or of 1 over t dt, is a natural log. This is the natural log. Technically, it's the natural log of TAI minus the natural log of T naught, but hey, TAI over T naught, you can use a log identity to arrange it like that. So I can say then that, yeah, by adding to both sides, my entropy at a given temperature, TAI for example, is going to be approximately equal to the initial entropy at temperature T naught plus Cp times the natural log of the ratio of temperatures, TAI over T naught. Let's see what that is for our values here for anorite. This is approximately equal to, S anorite was 89.5 joules per Kelvin per mole. That's a 5, really it is. Not a 6, not a 6. 89.5 plus the Cp is 83.1 joules per Kelvin times the natural log of the temperature 237 Kelvin divided by 298 Kelvin. And when I do that, I get 89.5 joules per Kelvin plus, what is this? Natural log of 237 over 298. I'll do that really quick. 237, 298, natural log. Minus 0.23 is this. And so times 81, or 83.1, sorry, 83.1, I get minus 19. Minus 19.0 joules per Kelvin. So that's approximately 70.0 joules per Kelvin. 70 joules per Kelvin, by the way, 70 divided by, oh no, 70.5, sorry. 70.5. 70.5 divided by 89.5. That looks like it's about a 21% difference. So minus 21%. That's a pretty big thing to call a constant. So I feel pretty good about saying, yeah, my entropy is going to change by a lot along the way. That I feel pretty comfortable that that was a good choice. What about delta S? What about my delta S? What would I have gotten there if I had done that calculation? And here I can use the same equations, right? I can integrate. I guess I just subtract the DSI version of all this. Oh, hey, this was supposed to be Cp of anorite, to be clear. That was anorite's Cp. If I just subtract the isildite version of the same equation, I'll find that the integral of, I can even say that I've done the integral, right? If a Cp's are constant, I can find that my delta AI of S at temperature AI, just for example, is going to be delta AI S of T naught plus delta AI Cp times that same natural log, T AI over T naught. And when I put in numbers for this, my delta AI for S, that was this minus this, gives me minus 4.9, I believe. Minus 4.9 joules per Kelvin. Plus my delta Cp AI. So this minus this gives me 1.1 joules per Kelvin times that same natural log of 237K over 298K. And when I do that, 237 divided by 298, natural log times 1.1, I get minus 0.25. So this is minus 0.25. What is that? Divided by 4.9. That's a difference of just 5%. So this will be approximately minus 2.5, 0.25 minus 5.15 joules per Kelvin. And that's only a 5% difference. So much better. This is this is much improved over what it was before. So I feel like that is, and a 5% difference. Maybe to the approximation level we're doing with all this stuff. Maybe that's not bad. A 5% difference. Who really cares, right? So yeah, that justifies at least a little bit what we did before. Looking at this. Having said that, we might also want to ask these same questions for the 5%. I feel okay about it. We might want to ask these same questions for the Ellendite-Iseldite boundary for this 893 Kelvin range. And if I do that, it's going to look the same, right? That boundary, the equations are going to look basically the same along the way. I could find. I don't need to redo this S calculation. I know that the entropies are going to change by a lot over that large range. What about my delta S? I'll find that delta S, I'm kind of squeezed over here, aren't I? Delta S IE at temperature, IE at that phase boundary equals, I'll put it down here, equals delta S IE at T naught. And then I'm going to use the same thing, plus delta, oh yeah, that's not my notation. I'm using the wrong notation. Put my IE in the wrong place. I've got to be consistent. Delta IE, my IE change in S, and my IE change in S at T naught, plus delta IE, that's an E really, of CP, times the natural log of T IE over T naught. Okay, lots of stuff going on there. This is just bringing this equation up, but putting it in our new case, in our new situation, bringing that up there. And I can put in my numbers, right? My difference in entropy between the two. I know I've written this down before, but the difference in entropy, I minus E, so this minus this is going to be, I should be able to just do that in my head, but I want to make sure I don't screw it up on a video. So 94.4 minus 98.1 minus 3.7 minus 3.7 joules per Kelvin plus my delta IE of CP. Again, I minus E, this minus this, that looks like a minus 2.5 times the natural log of my temperature ratio. And again, I'm using this as my estimate of temperature ratio here, 893 Kelvin over 298 Kelvin. It turns out that 893 divided by 298 is almost exactly 3. It's almost exactly triple the temperature. And if I take the natural log, that natural log is 1.09, because 3 is a little over 2.7. So that's 1.09. Actually, it's more like 1.10. This whole thing is 1.1. So that times 2.5 gives me 2.74. This is a negative. So this is minus 3.7 joules per Kelvin. Did I leave out the joules per Kelvin? Oh, that's terrible. Units. Minus 2.74 joules per Kelvin, which is approximately, so this minus 3.7 gives me minus 6.44. Minus 6.44 joules per Kelvin. That's a big change, right? That's something in the neighborhood of double what my initial 3.7 was. So I guess I could divide by 3.7, 74%. That's not good. 74% difference. I'm not willing to call that a constant. Probably you're not willing to call it a constant either. So that's a problem. Over here, the 5% difference, treating delta S as a constant, I felt pretty good about. Here, I don't feel good about that anymore. I feel like I need to do something to make this better. So I feel like we need to do better to get a better estimate. That 893 is not going to be a very accurate estimate because this wasn't very constant. So there are two things we can do. I'll tell you the real thing first. The real thing we can do is to just integrate our equation. If my delta S is this natural log, then I can say that delta G is just this integral, delta G T naught minus this integral of that function. We can integrate that function. It's something we can do. And what will that look like? I guess I can just write the integral down to begin with. An integral of delta IE S dt from T naught to TIE is going to equal, again, I'm squeezed over here, so I'm going to put the equal sign down here. That's going to equal an integral from T naught to TIE of delta IE of S of T naught dt. So that's a constant. That is a constant. That's the constant piece. Plus, and I'm still treating this difference in specific heats as a constant, even though that might be a bad approximation, plus the integral from T naught to TIE of delta IE CP times the natural log of T over T naught dt. That's kind of a messy function to deal with, but I guess I can write this down. I get my delta IE S of T naught times, I'm going to be lazy and write this as delta T. No, I've promised not to do that. I'm going to write it as TIE minus T naught plus delta IE of the specific heat times, and the integral of a natural log. Integral of natural log, you can look this up in tables. And it's a natural log of you've got a difference in temperature thing here. If we work this out, if you look it up in a table or something, you're going to find this winds up being T times the natural log, or TIE, I guess. TIE, natural log of TIE over T, and then minus, double checking my minus, yep, minus the higher temperature minus T naught. Okay, hey, that was kind of a mess. But basically it's T natural log of T minus T evaluated between the two boundaries or something. But oh, that's a T naught. We better not have any T's left. So okay, this gives me this messy function, right? This messy function showing up. This part's fine. This part's fine. But how do I solve for TIE when I've got some of it inside a log, some of it multiplying that log? It's a messy function. But this would give me my Gibbs free energy. I would find that my difference, i.e., in Gibbs free energy of T, of TIE would equal this whole thing. My, I guess I'd have here delta AI, or delta IE of the Gibbs free energy at T naught minus, minus the first term of this, my delta IE of the entropy at T naught times TIE minus T naught, and then I could probably simplify that, combine these together, couldn't I? Not going to worry about it right now. Minus that, and then minus that whole line, delta IE of CP times this whole, oh, it's so messy, TIE times the natural log of the ratio of temperatures, TIE over T naught minus TIE minus T naught. Oh my goodness. And that whole thing at the phase boundary should equal 0. And I'm supposed to solve for TIE. You can't do this. It's not a well-formed function. The functional form that the T times natural log of T thing in particular is the problem. There's like a product log function that's defined, but it doesn't make any sense. You can do this numerically. you can find a numerical value for this. And when I did it numerically earlier, I found, where did I do it? I found, doing this numerically, that I actually got a temperature for Ellendite of 714 Kelvin is the actual phase boundary of the Ellendite-Iseldite thing under this approximation. That's what I find if I'm more careful. So again, because this approximation was so far off, because delta S was so far from being constant over that wide temperature range, it meant that this approximation we got, the 893, was a very rough answer, and we had to do better. So it's disappointing that you can only do that numerically, right? That is a frustrating and disappointing thing. But maybe I'll say this: there is a shortcut you could try if you want to do better, but you don't want to go all the way to doing some messy solution with t log of t and all this sort of thing. What we could do is say, okay, fine. I know I don't want to do that whole messy thing, but I have found the S at my reference temperature, and I have found the S at my estimated higher temperature. And I estimated that range. I guess it doesn't go all the way. I found that S. What if I used the average of those two? What if I just said delta IES average? So that's going to be negative 3.7 joules per Kelvin minus 6.44 joules per Kelvin over 2. And what's that give me? Again, I should be able to do that off on my head, but make sure I get it right. I get negative 5.07 joules per Kelvin as my average delta S. So, okay, what if I just used that instead of doing this whole integral of a natural log thing? What if I just use that and use that as if it were the constant, right? Treat that as a constant. What if I say that delta G IE of T IE is approximately equal to what I had, delta, oh, I did my notation wrong again. Delta IE, my IE difference in that, delta IE of G of T naught, again, like I had down here, minus my whole thing, my delta IE of S average times TIE minus T naught. That was my, assuming it was constant, assuming a constant formula. And I can solve that the way I did before. I can solve by, let's see, and this whole thing, I remember that has to equal 0 at the phase boundary. So I can do what I did before. I can say, I can add this to the other side. I can divide by the delta S and add T naught. I'll find that TIE, if you do the algebra, I don't want to waste your time watching me do algebra, right? It's equal to T naught plus, and that wound up being delta IE of G, delta IE of G at temperature T naught divided by my delta IES average. And let's write this down. That's 298 Kelvin plus my delta G T naught. I had this written down just a moment ago, and forgetting it again, let me just pull it out of my notes instead. My delta G was minus 2.2 kilojoules. That's minus 2.2 kilojoules, so 2,200 joules, divided by my delta S average, minus 5.07 joules per Kelvin. That ends up being 298 Kelvin plus, the plus and minus cancel out, 1 over x times 2,200. That gives me 494 Kelvin, and that means, that's 298, get this right, 732 Kelvin. That 732 is still at 714. It's not the actual result, but it's better, right? The 732 would be maybe here or something. And so it's a better approximation. It's still not all the way there, but it's better. So this is just using the average. If your delta S, if your difference in entropys changes by a lot, you can make a significant improvement in your estimates by using the average of the two entropies and treating that as a constant across the range, and that'll get you an improved estimate for what that is. If I had done the same thing over here, by the way, for the Anarite Iseldite boundary, it would have just taken me to 238 Kelvin. So this one, that 5%, it really didn't make much of a difference at all. But over here, it made a big difference because it was a much wider temperature range I was extrapolating over. All right, that, I think, is most of what I wanted to say at this stage. Obviously, this whole story gets enormously more complicated if your specific heat changes with temperature and if that delta C changes with temperature. But again, the difference in CPs stays much more constant than either CP on its own would. So this is actually a much better approximation, and it works out pretty darn well. That's probably a good place to stop this video. And in the third one, that'll be my last one, and we'll take this data and we'll use the linear data, not these corrections, because we want it to be a self-consistent story. We'll use our original 893 and 237 Kelvin and related things to construct the full phase diagram of this in temperature and pressure and see how that shapes up.